In chapter number 8, we are discussing the join operators. After you have completed this lesson, you should be able to describe the SQL operators for joins, as well as list the possible access paths. In this lesson, we try to understand the execution plans related to join operations. The first topic that we're discussing in this chapter are the join methods. We're going to discuss what is a nested loop join, what is a sort merge join, what is a hash join, and what is a Cartesian join. If the optimizer has to build up an execution plan for a join statement, it has to take several factors into consideration. One of them being the access paths. If two tables are being joined together, it means that data needs to be retrieved from each table. Well, the optimizer has to think about what the most optimal way is to retrieve the data from the tables that are going to be joined together. So it has to decide on the access path, whether it's going to use full table scan or index scans, etc. The optimizer also has to decide on the join method. Is he going to perform a nested loop? Is he going to perform a sort merge? Or is it going to perform a hash join? And the optimizer also has to take into consideration the join order. If you're going to join table A with table B, the optimizer can consider to join table A with table B, but it can also consider to join table B with table A. So these are important factors that have to be taken into consideration whenever the optimizer has to build an execution plan for join statements. The optimizer has to decide on the join method. Now, a join defines the relationship between two row sources. It's also a method of combining data coming from two data sources and is controlled by join predicates, which define how the objects are related. And specifying a join predicate is imperative because if there is no join predicate or there is an invalid join predicate stated in the join statement, the result will be a Cartesian join, which is actually something that needs to be avoided at all time because it means that all the records of one table will be combined with all the records of the other table. Now, the optimizer can consider to use a nested loop join. The nested loop join is useful whenever small subsets of data are being joined and if the join condition is an efficient way of accessing the second table. So nested loops especially used when the tables are quite small if they need to be joined, in fact. Another join method is the sort merge join, which can be used to join rows from two independent sources, and it will be used especially if the data sets that needs to be joined are already sorted, in fact. The hash join is especially useful for joining large data sets. In that case, the optimizer uses the smaller of the two tables or data sources to build a hash table on the join key in memory. It then will scan the largest table, probing the hash table to find the joined rows. This method is the most optimal when the smaller table fits completely inside the available memory. Now, the first join method that is being discussed a little bit more into detail is the so-called nested loop join. And a nested loop join, as the name states it, it's a loop inside another loop. It means that one of the two tables will be considered as the driving table, and for every record from the driving table, we're going to try to find a match inside the other table, in fact. So for every row returned of the driving table, we're going to try to find a match in the other table, in fact. So the outer table or the driving table is a table from where we start, while the other table is called the inner table. And for each row in the driving table that matches the single table predicates, all the rows in the inner table that satisfy the join predicate are being retrieved, in fact. If an index is available, it can be used to access the inner table by row ID. So once again, for every record returned by the driving table, we're going to scan the others table to find a match of records to be retrieved. Now you also have the so-called nested loop join prefetching, in fact. And the idea of nested loop prefetching is to improve I/O utilization and therefore response time, in fact. Now, prefetching is not really being considered as a different execution plan. It does not affect the join order or the join method or the access method. No, it's actually an optimization under the covers, in fact. Now, what you have is without prefetching. What's going to happen is that if my driving table gives me a record, with that record, I will have to scan the other table, in fact. Then my driving table gives me another record. I have to then scan that other table. Now, it might be possible that if my driving table returns me a record, I have to access some blocks of the other table. If then my driving table gives me another record, it might be possible for that other record that I'm going to scan exactly the same blocks again of my inner table, in fact. This is going to increase the number of blocks being accessed, which can also induce an increase in I/O operations, in fact. However, what you have is the prefetching is an optimization under the covers, is that my driving table gives me a record, but I'm not going to necessarily immediately start to scan blocks of the other table. No, I'm going to obtain a couple of records of my driving table, in fact, and then scan my other table, the so-called inner table. So it means that I'm going to reduce the number of blocks that need to be accessed, in fact. So with data block prefetching, the system delays data blocks reads until multiple rows are ready to be accessed, in fact. And then your system will retrieve multiple data blocks simultaneously rather than reading one single block at a time. But once again, it's not being considered as a different execution plan. It's simply an optimization under the covers to improve the I/O utilization and therefore the response time. Then you have the sort merge join method. Now, sort merge joins perform better than nested loop joins for large data sets. Nested loops are quite optimal if you're going to join smaller data sets. So in a sort merge join, there is no concept of a driving table. But how is a sort merge join being executed? Well, if you're going to join two tables, it's going to first get the first data set from the first table and sort it upon the join columns. Then it will get the second data set and sort it upon the join columns. And then for each row in the first data set, find the start point in the second data set and scan until you find a row that does not join. So this is, if the two data sets are already sorted, it's very easy to merge them together. This will be reflected as the sort merge join within your execution plan, in fact. Now the optimizer can select the sort merge join over an hash join for joining large amounts of data if any of the following conditions are true. So if the join condition between two tables is not an equi-join, he will not go for an hash join but more for a sort merge join. And if the sorts that are required have already been done by previous operations, the optimizer will favorize the sort merge join. The third method for joining two tables together is the so-called hash join, in fact. And what you will have is that with a hash join, the system reads the first data set and builds an array of hash buckets in memory. And such a hash bucket is a little bit more than a location that acts as the starting point for a linked list of rows from the build table, in fact. Then with the help of the hash buckets, in fact, the second row source is being hashed and checked against that hash table, in fact. Hash joins are really efficient if large amount of data must be joined, in fact, or a large fraction of a small table must be joined. A Cartesian join simply means that all the records of one table are being joined together with all the records of the other table. And a Cartesian join will be performed when one or more of the tables do not have any join conditions to any other tables in the statement, or an invalid join condition has been specified. Like I've said, this will result then in a Cartesian product, which is a data set that has combined every row of one table with every row of the other table. So if my table employees has 1000 records and my table departments also has 1000 records, the Cartesian product will be a result set of 1 million records. That's why Cartesian joins are generally not desirable. Now, the second topic that we're going to discuss in this chapter are the join operation types. We'll see what is an acqui join, what is a non-acqui join, what is an outer join, what is a semi-join, and what is an anti-join. Now, the join types that we're going to discuss is actually the result of a join operation that combines the output from two sources. The second topic that we're going to discuss in this chapter are the join operation types. We will discuss what are acqui joins, non-acqui joins, outer joins, semi-joins, and anti-joins. Now, a join operation combines the output from two row sources and returns one resulting row source. Like already mentioned previously, join operation types include acqui joins or non-acqui joins, outer joins, semi-joins, anti-joins, and star joins. The second topic that we're going to discuss in this chapter are the join operation types. A join operation combines the output from two row sources and returns one resulting row source. Now, join operation types include the following. You have acqui joins and you have non-acqui joins. You have outer joins, semi-joins, anti-joins, and you have the star join. Now, what is the difference between an acqui join and a non-acqui join? This has nothing to do with the join methods. So you can have the hash join, you can have the sort merge join, you can have the nested loop join. But what makes a join an acqui join or a non-acqui join? Well, if you're going to write a select statement where you're going to join two tables, but in your join condition you use the equality operator, we say that you are doing an acqui join. However, if you write a select statement where you join two tables, but the join condition is not based upon an equality search, then we call this a non-acqui join. That's the difference between acqui and non-acqui join. An outer join is a join that returns rows even if no match is being found, in fact. So maybe I'm scanning one table, but I do not find a match in the other table, in fact. The row is still being returned, in fact. Now, whenever outer joins are being used, this will be reflected in the execution plan via the option that an outer join is being used, whether it's done via nested loop, a merge join, or an hash join. With a semi-join, only the first match will be returned. For instance, if you write a correlated subquery with the exist query, you only want to find out if a value exists in another list, in fact. You do not care how many times that it exists within the list, but you simply want to find out if it exists. So if I have my table depth and I want to find out if the value of 10 appears in table emp, well, it says no, it says yes, and I can stop the scanning, in fact. because I have found value 10. I do not have to scan any further if there is another value 10. I just want to find out if value 10 exists in table emp. That's a so-called semi-join. Then you have the anti-join, and the anti-join is actually the reverse of what would have been returned by a join, in fact. Like, for instance, you have here a select statement where you want to obtain the records from departments, but of which the department ID does not appear in table employees. Well, actually what he can do is the optimizer can say, I can join departments with employees to find the matches, but for the records that I did not find a match, those records I will return. The records for which I found a match, they will not be returned. And that's going to be shown in the execution plan as a so-called anti-join. Now there are a couple of quizzes that you can complete for this chapter about the join operations. The first quiz is, the optimizer uses nested loop joins when joining a small number of rows with a good driving condition between two tables. Well, the right answer is A. This is true. When a small number of rows needs to be joined and you have a good driving condition, in fact, the nested loop is probably the most efficient way to perform the join operation. Which type of join is used when one or more of the tables do not have any join conditions to any other tables in the statement? Is it a hash join, a Cartesian join, a non-equi join, or an outer join? Well, the right answer is B, the Cartesian join, because if you write a select statement where you want to join two tables but you do not specify a join condition, you will know upfront that this will result in a Cartesian product. Which type of join looks for only the first match? Is that the hash, the Cartesian, the semi, or the outer join? Yeah, the right answer is the semi join, which only returns the first match. And then in a hash join, which row source is used to build the hash table? Is that the biggest row source, the smallest, the sorted, or the unsorted row source? Well, if you talk about sorted and unsorted, you talk about sort merge joins. With a hash join, it's the smallest row source, the smallest table that will be used to build a hash table. Now, in this lesson, you have learned how to describe the SQL operators for joins, and you have learned how to list the possible access paths. There are some exercises that can be made for this chapter number 8. The exercises cover the different join paths for better optimization. Workshop 8 of the SQL Tuning for Developers course. So in this workshop, you will review parse time reduction strategy, test without cursor sharing, use cursor sharing, use user-defined bind variables, and load SQL statements into an SQL plan baselines. This is a listing of all the scripts that are needed for this workshop number 8. To make your life easier, open all of those script files beforehand in the order as specified in the activity guide. All of those script files can be found underneath the workshops folder. So you have identified a slow running SQL statement. It was executed 555 times in a certain time period. You have noticed that a different literal was used in each execution. This caused the system to parse the same statement 555 times with a high parse time, which is not efficient. What tuning strategy could be used? So let's say you look at the statistics that have been captured while you have traced that session, in fact. Now, what do I see is, in order to review the parse time reduction strategy, I'm seeing that the total elapsed time spent parsing is 300.83 seconds. What is the elapsed time spent executing? That was 0.78 seconds. It was only 85 seconds of elapsed time spent on fetching. Would normal query tuning techniques that alter the execution plan help? No, because your biggest portion of the time spent on getting the result of the execution of that statement is due to the parsing. So, would reducing parse time help? Parse time reduction strategy can be used when you have determined that the query spent most of its time in the parse phase, which is here definitely the case. Now, how can you reduce parse time? Well, you have two options. Or you're going to make use of bind variables so that statements can be reshared, or you can make use of adaptive cursor sharing. You can also try to reduce the parse elapsed time. Now, if the CPU time dominates the parse time, then check common observations like dynamic sampling being used, queries that have many in-list or operators, or that you're doing queries upon partition tables with many partitions. If the wait time dominates the parse time, then check for the waits for large query text to be sent from the client. Now, in this workshop, we're going to choose option number 1 to reduce the number of hard parsers by trying to share our cursors, eventually to reduce the total parse time. Now, the first thing that you will need to do is in SQL Developer, make sure that you have set up a connection to be able to connect as the SH user to your database environment, and review the two SQL statements in the script file WS08. There you're going to consider the use of bind variables to reduce the parse time. So if I'm taking that script file, you see that it's twice the same select statement, except that in the first select statement, the country ID is 52790, while in the second select statement, the country ID is 52787. You see that the literal values are different. So for Oracle, these are two different statements, means that each statement needs to be parsed one time and executed one time. So you will have a parsing and an execution for that select statement, and a parsing and an execution for that statement. Now, which column is a good candidate for a bind variable? Yeah, this is obvious. This is the country ID column because you're looking for a literal value to reduce the parse time by means of sharing cursors. We're going to replace the literal values by means of bind variables. Now, first of all, we're going to determine the distribution of the distinct values within this candidate column to be combined with bind variables. Now, I'm going to take this script file, w8s2c.sql, and you're going to execute that query as the SH user to actually have a look. Okay, what are the distinct values within that column country ID, and also calculate the amount of percentage that they appear inside that table. Now, the two values that we're going to work with is 52790 and the other one is 52787. Now, if I take a look at 52790, 33% of my rows contain that country ID, while only 0.1% of the rows in my table contain country ID value 52787. So there are a lot more 52719s than you have 52787s. This is a clear example of data skewness. On such columns, you should consider the creation of a histogram. You can do this by running this script file that uses the procedure gather table stats of the package dbmstat to calculate, in this case, an histogram upon the country ID. So I'm going to take that script file, take sh connection and execute this. Now, then I'm going to look into user tab columns to see if there are histograms upon the columns of table customers. My column of interest is the country ID column. And what do I see is, if I can find it over here, the country ID column has a frequency histogram and there are 19 buckets. Now, a frequency histogram with 19 buckets, that means that there are only 19 distinct values inside that column country ID. Now then what we're going to do is we're going to create an index that will index that country ID column by executing W8S2E script file. To do this, create the index as user sh upon the country ID column of that customer's table. Execute this. The index has been created. Then what we're going to do is, for the query that is using the literal value 52790, we're going to determine the execution plan. This is a value that appears in 33% of the rows of my table customers. I'm going to execute it via the script file W8S2F. So here my script file W8S2F, SH connection. I'm going to execute this. And what do I see is that as an execution plan, you see that he's doing a full table scan of the customer's table. Now, this is a very good execution plan because this is going to retrieve 1/3 of my table. Going via the index would not be the most efficient way to do so. But then they ask me to review the execution plan for the statement that is using the literal value 52787 by running W8S2G script file. So I'm going to take the script file, sh connection. Now we know that this value only appears in 0.13% of the rows of my table customers. I'm going to execute this. And what do I see is that to access the customer's table, to look for 52787, that he has taken the index, which is probably the most efficient way to only return 0.13% of the data out of that table customers. So why are the execution plans different when I'm looking for the value 52787 and 52790? Well, the thing is that he sees that you're using literal value 52790. He sees that there's a histogram upon the country ID column and sees that it appears in 33% of the data. Optimizer says, let's go for the full table scan. While if I'm searching for 52787, the optimizer sees via the histogram that that value only appears 0.13% in the rows of that table. It would be much more efficient to go via the index. Now, how many hard parses took place? Because both statements are different because of the literal value, I will have 2 hard parses. Now, we want to reduce the number of hard parses, and that's something that we're going to do in task number 3. So, both statements, they are hard-coded. So, let's say that we cannot adapt the source code, but we want to make use of bind variables. But I cannot adapt the source code. Well, what you can do is you have the possibility to play with the parameter cursor sharing to force Oracle to replace literal values by means of bind variables. Now, what you will need to know is that if you, by the cursor sharing parameter, or you're going to change the source code to use a bind variable, it's only at the first execution of that statement with that bind variable that Oracle has a look at the value of the bind variable that you're using. Based upon that value, he will calculate the selectivity and the cardinality and come up with an execution plan. If then you're going to execute that statement a second time, a third time, but with a different value for the bind variable, he will find an exact match of that statement in the shared pool, and he's going to reuse that same execution plan as well. But if in that column that you combine with that bind variable, you have skewed data distribution, and even if you have histograms, this can lead to the utilization of a suboptimal execution plan for certain values of the bind variable. Now, what you can do is, if you do not have access to the source code and you want to use bind variables, you can actually put your parameter cursor sharing to false. The default is exact, so the statements have to be exactly the same for the statements to be able to be shared. Now you can put it to false, and to force you dictate Oracle to replace literal values by bind variables, in fact. Now, what you can do is, you have a script file w8s3a.sql. It gives you the possibility to create an after log on trigger that fires after somebody logs onto the database, and if that user is equal to sh, then it will set the session to set cursor sharing to exact or false, whatever value that you're going to specify. So you have a script file w8s3a. So here w8s3a.sql with the coding to create such an after log on trigger that will test if it's user HR that logs in, and if so, to put the cursor sharing parameter then to false or to exact. So let us run that script file, and what I'm going to do is I'm going to replace this value, going to replace it with exact, which is the default, in fact. Make sure that you run this as the sys connection. So I'm running the script. That trigger has been created and compiled successfully, in fact. Now, I'm not using for, so literal values are not going to be replaced by bind variables. And then I have to run that script file, and also that script file, to see whether system bind variables were used or not, in fact. So what I'm going to do is, so I take the script file w8s3c.sql, where I'm not changing the SQL statement, so I'm using literal 52790, and see if it's being replaced by a system bind variable. If I take this script, sh connection, I run the script, what do I see is, if I look at the output, you see that it's not being replaced by a bind variable, and he comes up with a full table scan. Then I'm going to take the file w8s3c1 sh connection. I execute this, and what do I see is that it's not making use of a bind variable. So if I would have put it to false, you can test this out, you will see that those literal values are being replaced by a bind variable. You run this script file w8s3d to drop that trigger. I'm taking this one, this connection, and we're going to drop that trigger. Now, what we're going to do now is we're actually going to adapt the source code ourselves and replace the literal values by bind variables. So what we're going to do is I'm going to run w8s4b.sql, create a bind variable country ID, give it the value 52790, and execute this select statement with that country ID value. This is the very first time I'm going to execute that statement. So w8s4b, I choose sh connection. I'm going to run this. Now, what's happening is, this is the very first time that I'm executing this particular statement. It's the very first time. It needs to do a hard parsing, and the optimizer has to come up with an execution plan. Well, the optimizer is going to have a look. yeah, but what value are you using for the country ID column? And he sees you're using 52790. He's going to use that value to calculate its selectivity and cardinality in order to determine the most efficient execution plan. This is happening only one time, and that's at the first execution of that statement. This mechanism is called bind variable peaking. And what do I see is, based upon 52790, he said we're going to do a full table scan upon the customer's table, which is okay because 33% of the data inside that table has country ID value 52790. But then what we're going to do is we're going to execute the same query again, but we're going to change the bind variable value before we execute to 52787. So let's have a look at this. So I have here 52787 and execute the same statement. That statement is found inside the shared pool because I already executed it before, but the bind variable value is now 52787. I'm going to execute this as sh, execute this, and what do I see is, yeah, that he's using the index range scan. Now you could say, yeah, we're using bind variables so that statements can be shared, so that the execution plans can be reused. So we're going to reduce parse time, because with the second and the third and so forth execution of that same statement using a bind variable, we don't need to do that parsing anymore. But I still see that he comes up with another execution plan. Well, this is actually the effect of adaptive cursor sharing. If you have a statement that uses bind variable, but in combination with a column that has a histogram, whenever you execute that statement, in this case the second time, it's going to see, yeah, but you're using another bind variable value. I'm seeing, because of the histogram, that there is skewed distribution in country ID. I'm going to evaluate anyway if I cannot find a better execution plan for 52787. Because if he would not do that, he would reuse that full table scan that was generated by the first execution of that statement. But that means that you're going to use a full table scan upon table customers to retrieve only 0.13% of that data, which is of course not the most efficient way to get that data. So what you see here was the effect of adaptive cursor sharing. Now, what you can do is you can use SQL Plan Management, which makes use of SQL Plan Baselines. Now, what you can do is you have the possibility to load the two plans that have been found in step B and in step C into the SQL Plan Baseline to maintain these plans over time. You can do this by running the script w8s5a.sql and review if they have been successfully loaded via the script w8s5a1. So I'm going to take that script file w8s5a, that's over here, in order to load the execution plans of that statement using the bind variables. Now what you will need to do is, first of all, I have to look up what is the SQL ID for that statement that is using a bind variable. I'm going to copy this and I'm going to paste this over here. Then what I need to do is I also have to fill in here the plan hash value. So I have to pick up the SQL ID and I also have to enter the plan hash value. And what I'm going to do is, let's see here, the plan hash value is this one. Control C, W8S5A. I'm going to replace this over here. 1 moment. Of course, like this. I'm going to copy this, Control C, and I'm going to paste it over here. Take the SH connection. I'm going to execute it again, and then I'm going to use the script W8S5A1 as the SH connection, and I'm going to execute this. Now, of course, make sure that you also load that second execution plan. So what I'm going to do is I'm going to, for the 52787, I will take the SQL ID. So I say Control C. I'm going to copy paste the SQL ID over here. Yes. Here I take the SQL ID and I'm going to paste it over here. And I'm going to wipe out this, go to C and take here that plan hash value. Control C and copy paste it over here. And I'm going to execute this. And then I'm going to use W8S5B to see if the execution plans for that statement using that bind variable have been uploaded as an SQL plan baseline. And you see that both plans for that statement using that bind variable has been uploaded. Practices for lesson number 8, optimizer join operators. In the exercise of chapter number 8, you will examine 3 SQL statements and compare the different join methods for each statement. So in the practice, you will explore the various access paths that the optimizer can use and compare them. You have the possibility of exploring different scenarios, each of which is self-contained. All necessary scripts are still found underneath the directory access path. Now first we will have to prepare our environment and grant the appropriate roles and privileges to the users OE, SH and HR. So what you're going to do is, in your SQL developer, you're going to open the script file join setup. Make sure that you choose the sys connection. And you're going to execute the statements within this script. You see that roles and privileges are being granted to the users OE, SH and HR. Then they ask you to create a connection named HR if you did not create that yet in practice number 2. But that's something that is already shown in that lesson concerning the activity of chapter number 2. Then the first case study in the join method is the so-called nested loops join path. Now nested loops work well with very small tables and larger tables with indexes on the join column, and in at least one table produces a small row source. So they ask you to run a particular select statement and auto trace it, which you can find in the script small tables join that you have to execute as the HR user. I'm going to look up small tables joins, where there is a join between table departments and table locations. And we're going to execute and auto trace this as user HR. I'm going to auto trace this. And what do I see is that a nested loop has been chosen as being the most efficient way to perform this join. This nested loop comes with a cost of 5 plus the number of consistent get. That means the number of blocks being accessed to perform this join is 11. This is the default join method that is being chosen for this particular select statement by the optimizer. So the cost is low, This is expected because both tables in the query are very small. Then we're going to run another script where we're going to do the same select statement, but we're going to force the optimizer to use the hash join method by means of hints. So what you need to do is you have to look up here the script file small tables hash join. Make sure that you launch it at HR, and you see that there is a hint where I'm telling the optimizer to join departments and locations. You have to use the hash join method. And I'm going to auto trace this, and what do I see is that this hash join has a higher cost than the nested loop. I can see that the hash join has a cost of 6, while with the nested loop the cost was only 5. So we forced the optimizer to use the hash join method. The cost is higher, and I will also see that with this join method, when I'm looking at the execution statistics, that also the number of blocks that have been accessed is higher than with a nested loop. And then they ask you to run another script file where we join both tables together, but with the sort merge join method by running the statement inside this script file. So what you do is you look up small tables merge join, launch it of course as user HR. And you see that there is a hint where I'm telling the optimizer you have to use the sort merge join method. And I'm going to execute this. Now, first of all, what do I see is that the number of blocks that he needs to access to perform this join via the sort merge join method is 8, which is less than with the nested loop. However, the cost is higher for the merge join than you had for the nested loop, because the cost of the nested loop was 5, and that's because in that cost there is also the additional cost of sort operations that need to be performed, and that is not included inside the consistent. Case number 2 is the merge join. The merge join is a general purpose join method that can work when other methods cannot. The merge join must sort each of the 2 row sources before performing the join. Because both row sources must be sorted before the first joined row is returned, the merge join is not well suited for use with the optimizer mode set to first rows. And I will ask you to run a select statement via query oequery.sql as the user OE. So what I'm going to do is I'm looking up that script, OE query. Make sure that you execute it as the OE user. And I'm going to auto trace this. And I'm seeing that the optimizer picks as the most efficient join method the so-called sort merge. And the cost of that merge is a total of 6. But then they ask you to run a script to do exactly the same select statement, but forcing the optimizer to use a hash join by the script oequery hash. So what I'm going to do is I'm looking up oequery hash.sql, open it. You see the hint where we're forcing the optimizer to use a hash join. Make sure that we execute it as the OE user, and we're going to perform the auto tracing in fact. Now what do you see is that the hash join also has a cost of 6. But when I'm not forcing him to choose a particular join method, he goes for the sort merge join. Well, what you will have is, if you're comparing the estimated cost of the hash join with the sort merge join, it's exactly the same, but the additional sort required by the sort merge join method does not raise the cost enough to cause the hash join to be chosen by the optimizer. And then they also ask you to do the same select statement, but by forcing the optimizer to perform a nested loop. So what you're going to do is you look up the script OE query NL. Make sure you execute it as the OE user. I'm going to auto trace this. And there you can see that while I'm forcing him to use the nested loop, that the total cost is 148, which is extremely high compared to the two other join methods. So it's much higher than either the hash join or the merge join method. We have seen in the first case that nested loops method depend on either very small tables or indexes to be an efficient access path. In case number 3, we're going to observe the hash join method. The hash join method performs very well on large row sources and on row sources where one row source is smaller. The hash join method will build a hash table in memory on the smaller of the row sources. The procedure then reads the second row source, probing for the hash value in the first. Because the rows are joined as soon as a match is found, the hash join method is also preferred when the optimizer mode parameter has been set to first rows. Now they ask you to run this select statement by launching that sh query script file as user sh. So I'm going to look this up. So I'm looking for sh query. Make sure that it gets executed as user sh. Do the auto tracing. The third and final case of this chapter number 8 is the observations on the hash join. The hash join method performs very well on large row sources and on row sources where one row source is smaller. The hash join will build a hash table in memory on the smaller of the row sources. The procedure then reads the second row source, probing for the hash value in the first. Because the rows are joined as soon as a match is found, the hash join method is also preferred whenever the optimizer mode parameter has been set to first rows. Now they're asking to run this select statement by launching the sh query script file as user sh. So I'm going to look up that script sh query. I'm going to make sure that I execute it as the sh user, and I'm going to auto trace this. And you see that the optimizer has chosen a hash join, and I can see that the cost of that hash join is 33. But then they will ask you to run the same select statement, but forcing the optimizer to perform a nested loop. You do this by launching sh query NL script file. So I'm going to look up that statement, sh connection. I'm going to perform the auto trace, and you see that I forced him to use a nested loop. But if you take a look at the cost of a nested loop, it's far more bigger than the cost that we have seen for the hash join. And then I will also ask you to run that same statement again, but by forcing the optimizer to go for the sort merge join. You do this by launching the query sh query merge. So I'm going to look up that script, sh connection, and I say auto trace, and you see that I forced him to perform a sort merge join. But if you look at the cost of the sort merge join, you see that it's even bigger than the nested loop. And the nested loop was already far more bigger than the cost calculation that it did for the hash join.